right, so we got Cole's breadboard here, and for the moment I've removed the power to the Arduino to just use the barrel plug. And if we fire it up, they are, because I'm an idiot. Okay, so we got our clock going. Yeah, okay. So that looks pretty good. Of course, you can't really see anything on the LCD on the camera here. I'll probably have to adjust the contrast, but I'll just leave it as is for right this instant. Okay, and I'm going to go ahead and unplug it, and I want to talk about the programming part here. So, so what I've got is I've got here, and I've got a sample program which I need to open. So let me open up, and okay, we want to go to desktop 6502. I'm going to just start with this one. Okay, so we've got this sample program, and let me change the screen color so you guys can actually see what's going on. All right, so we want themes. We'll do one light. Okay, so that's a little bit better. And then we'll do, oops. There, okay. And then we'll put this one on the left. Okay, good. So I've got this sample program that Ben wrote for one of his, or for this machine, and I want to kind of talk through what the details are of it, and then also how we actually get this onto the EEPROM and such. Okay, so basically the not compiling, but the assembling procedure, and then the EEPROM part of it. Okay, so at the very beginning of it is where you can define basically macros for placeholder stuff. So for example, if I've defined here port A and B to be these addresses and DDRA and DDRB, anytime I use DDRA in my program, the assembler will actually replace that with the actual memory address. Okay, so the memory addresses here are 6,000 through 6,003, and those were not chosen completely arbitrarily, but somewhat arbitrarily. Why did we pick 6,000 through 6,003? Because it's not in the range of stuff that's already been used. Okay, so what already has been used in terms of address space? We've used addresses. Well, where's our RAM? And where's our ROM in address space? Eight thousand up was the ROM, okay, and everything underneath of it, half of that from 0 to 3 FFFF or 3 FFF, right? That quarter, that bottom quarter, was RAM. The top half was ROM, and then the second quarter, so the stuff between 4,000 and 7 FFF, doesn't have anything attached to it except that's where the 65C22 is attached. Okay, and the 65C22 has 4 things that we care about. Okay, it has basically it's port A and port B. Okay, and then the data direction registers for the A and the B stuff, which are at, we've tied all of those to 6000 through 6003. Okay, so these are on the 65C22. Basically, if I want to send data to the A bus on the 65C22, what I do is I send the data to address 6001, and the 6522 actually sends that to its A bus. Okay, so so this technique here, right? What we're doing is called memory mapping. The processor thinks that it's writing to a particular location in memory, but what it's actually doing is it's sending it to another chip that we configure in an appropriate way. So how do we read, write, or whatever? What do we need to do? Well, this is what the DDRA and DDRB memory address is for. Okay, basically those are going to control whether or not we are reading, writing, whatever, and so that tells the 65C22 whether or not the A bus or the B bus on it is going to be reading, writing, whichever. Okay. Now, in our case, what do you mean? Well, both buses can do both functions, right? So, well, okay, okay, let me back up. The 65C22 doesn't have to have either one being write or read. They can both be writing, they can both be reading. One could be one could be the other. Okay, so then now that's a general thing. How is it actually, though, in terms of the machine that we've wired up here? How are we using the 65C22? Okay, well, some stuff's going to the screen, correct? Okay, and for the most part, we would be writing to the screen rather than reading from it, although technically we can. Okay, whereas the buttons we would be reading from because we are pressing them and then things happen. Okay, so which you can't, yeah, exactly. You can't write to a button. So you could tell the chip to write to the button, but it's not going to actually do anything, right? That just doesn't make sense. Okay, so all of that is going to get controlled, right, with whether or not with these control registers, and there's certain values that you have to basically push to them in order to get it to do something. Okay, so now the what's nice here is that you can actually configure each separate pin to be input or output, okay? Which is actually what we're going to have to do here, because how many pins do we need to control the LCD? It's more than 8, okay? Now, but we only have 8 lines on each of the A and the B buses, okay? So what we're going to do is use some of them, okay, use all of the B bus and some of the A bus all collectively for the LCD, okay? And then the remaining things that are on the A bus we'll use for the buttons. Uh, no, these are where the 65C22 is, which sits in between the processor and the LCD. Okay, that's how you get to it, and then it communicates with the LCD or the buttons, right? So we can't, like, this is the thing, and of course modern computers are like this too, right? The processor is not directly attached to everything, right? There's interface chips in between it and other peripheral devices, and that's what the 65C22 is doing for us, okay? So on your modern computers, not all of the hardware, in fact, most of it is not directly attached to the CPU. Some is, but not all of it, okay? Okay, so so I've got this program, right? We've got some macros up at the top, and the convention in the old school assemblers of the day was that anything that's in hex has a $sign in front of it, anything that's in binary has a % sign in front of it, and anything that is an immediate value has a pound sign in front of it. This means, by the way, that you can have pound $sign if you wanted to specify a specific number in hex. If there's no $sign, what does that mean? It's in base 10, and the assembler converts it for you, okay? So if you wanted to address or put the number 17, you could type 17 and not have to put it in hex, right? You could put it in hex, but you didn't have to, okay? So how would you say that you want it in hex, or what you're putting is in hex? You'd put a $sign in front of the number, okay? And then the pound is for immediate values, okay? All right, so that good? Hashtag is immediate, dollar is hex, and % is binary. And then you can have hashtag, an immediate that's either in hex or binary or base 10, right? So for example, here on line 21 there, right, the instruction is to load the A register, the accumulator, with the number 0. In that case, obviously, it doesn't matter if I specify it in hex or not, because 0 is still 0, right? But I could do it either way. Okay, so now, as for the program, okay, this line 10, is something that we never had to do when we were doing this in ARM, okay, which is to specify where the thing is going to go in terms of its memory, okay? And we do that by saying org 8000, okay? And so this tells the assembler that the base address for the program is going to be at address 8000, and to do everything relative to that, okay? And we didn't have to do this when we were doing stuff with the ARMs, because we had an operating system that was going to load the program into wherever it wants in memory and take care of all that for us. But we don't have that now, right? Add. Yeah. So it doesn't, there's no operating system, and hence we have to hard code where does our program start. Okay. Now, why 8000? That's where the ROM starts. Yes. Okay. Now, that said, though, there's one other thing that we have to do, which is if I look down to the very, very, very bottom, okay, and at org FFFC and org, or at FFFC and FFFD. So this is specific to the 6502, okay? When you first fire up a 6502, it's going to go someplace to find its first instruction. Where is the memory address where it finds where to go for the first instruction? No, that's where it goes. But where, so, okay, that's what the memory address is, okay? But where is that number 8000 recorded? It's recorded in FFFC and FFFD. Those two memory addresses are the reset vector, okay? So pull out your 6502 data sheets, or pull it up on the computer, okay? And look at, let's see, page number 12. Okay, so page number 12, and in the PDF it might be a different actual page, but it's labeled 12. The 6502 has 3 vectors, okay? And those vectors are the location of code for an interrupt, handler, the location of code for the non-maskable interrupt handler, and the location of code for the reset vector. Okay, so after the processor fires up, it's going to go to FFFC and FFFD. Those are the reset vector locations, and whatever it finds there is going to be the memory address that it goes to load in the very first instruction of the program. Okay, so if we want our program to start in memory at address 8000 hex, then what do we need to put in FFFC and FFFD? 8000. Okay, and that actually would be 000 or 80 because it's in backwards order, but you guys are used to that issue by now. Okay, so processor fires up, it goes to FFFC, FFFD, and says, oh, 8000. That's where I'm supposed to start executing code, and then it jumps to 8000 and starts executing whatever code it finds there, okay, which will be our program. Okay, so does that make sense? They are in the ROM. Okay, so this is why in our program here at the very bottom, I have to say, okay, starting at address FFFC, I want to put a word which is reset, and where is the reset vector? FFFC. Okay, so he has defined FFFC up at the top to be what he's calling reset. Okay, and then the other thing we need is the address. Well, okay, how big should our ROM image be? How big does it need to be? Well, how big is our ROM? 32K, right? And so our image that we have to, the binary image that we write to the ROM chip must be precisely 32K. Now, if we start everything at 8000, then that means that what's 32K up from that? We have to fill 32K worth of stuff. Okay, so if FFFC and FFFD have our reset vector, we're 2 bytes short because we need to have something at FFFE and FFFF. And what are we going to put there? Right, okay, the interrupt request, the interrupt handler, which for right now will just make all zeros. Okay, eventually that will be different. The interrupt, all zeros, or the interrupt request? Okay, we'll talk about the interrupt stuff next time. Basically, the interrupt request is going to handle, like, if I hit a button on the buttons, okay, then I want the processor to stop what it's doing, deal with the fact that I just hit a button. Once it's dealt with that, then resume its previous set of instructions. Okay, so in terms of, like, imagine playing a game, when you hit a button on the controller, it's going to trigger an interrupt that's going to say, okay, which button just got pressed and what should I do accordingly? And then once it's dealt with that, then it resumes executing the code that it was before. Now, in terms of a game, this all happens very quickly because you're interrupting lots, right? And so that's the interrupt request. And then there's also the other one, which is the non-maskable interrupt. And the difference between those is interrupting can be turned on and off. Okay, so the processor could say, or a piece of code could say, all right, I need to not be interrupted for the next 10 instructions. So I'm going to turn off the interrupt channel, do what I need to do, and then turn back on the interrupts when I'm finished. Okay, and then if an interrupt occurs while it's in that little block of code, it will not deal with it until after it's done with the chunk that it was working on. Okay, a non-maskable interrupt, on the other hand, cannot be turned off. Okay, so the difference here is you want to use interrupts for things that are important but not show-stopping, and non-maskable interrupts for things that absolutely must be dealt with right that instant, no matter what. Okay, and which we'll talk about more later. Okay, so so this stuff is there for two purposes. One is we have to put the reset vector into our ROM so that the processor knows where to jump to actually start doing stuff. And then the last word of all zeros is just to pad it so that it's a 32K image. Okay. Now, eventually, when we put in interrupt handlers, that last 0000 will change to something wherever our interrupt handler is. But we don't have that yet. Okay. So, in terms of the code here, what is it basically doing? Okay, this is the world's jankiest Hello World program. Okay, and so what does each one of these things do? Well, it's going to load Hello World by taking the H. Okay, that's a piece of data, storing it to the thing, and so on. Okay, so this is like the world's slowest way of writing Hello World, but it will work theoretically, and we'll find out if it works with Cole's board or whether or not we get the magic purple smoke. Okay, okay, so let me get to the appropriate directory. Okay, and I've got here the hello world.s. Okay, so I need to do vasm old style. Okay, so this is the assembler we're going to use. This is the same one he uses in his videos. There are lots of different 6502 assemblers, but this is the one we're going to use. All right, what we want to do output by using to a binary file, and we do that with the -fbin option. Okay, and oops, sorry, I've got a spam bot on the Discord. I mean the thing here. Or I mean on Twitch. Okay, he's banned. Okay, banhammer. Okay, so I want to output a binary file, okay, because that's what the EEPROM programmer will take. And then in this case, I'm doing hello world.s, okay, and welp. Hold on, let me try. Well, crap. All right. Why is that not working? No, it has nothing to do with your board. Damn it. Okay. Well, here, let me try the other program. Yeah, okay, so this is a problem with the assembler. I don't know why this isn't working because this is the exact code that he's. Okay, so basically what it's complaining about is the this .org thing, which means I probably have screwed up something about the um, Okay, let me double check here. So we've got 6502 CPU backend, old style, okay, binary output module, that's damn it. Okay. Oh well. So the assembler is not, I wonder if he used a different version. So the this directive, it's basically complaining it doesn't know what that mnemonic.org is. And so let me look at the um, the manual. Okay, hang on 1 second. Let me. Oh, okay. I have an idea. Okay, so I think the assembler got updated to not use the dots. All right, so let's try that. There we go. Okay, so yeah, so it looks like when Ben wrote this code, the the assembler was expecting a dot in front of org, and so I've got the manual open and I'm looking at the old style section of it, and it doesn't have the dots anymore. Okay, so that explains that, and we'll see that it all worked here. Okay, and now if I do, I've got here a dot out, which is a 32K file, okay, and I didn't specify the file name, but if I cat, right, it looks like a bunch of gobbledygook to me, right? But if I hex dump it, okay, what do we see here? Well, a whole bunch of stuff that still is somewhat gobbledygook, but what is that? Okay, this is my image file. Okay, so the binary image, but what are all of these things, right? So A9, FF8D, blah, 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 right? So what is A9FF? Yeah, you see A9 appearing over and over and over again, okay? That is the encoding for the load A instruction, okay? If we go back to our source code, what was the very first instruction that we did? LDA, and then, so all ones, okay? So in hex, what is that? The all ones is FF, okay? And what is the instruction that we're doing? So what does the mnemonic LDA do? What is that instruction? Load the accumulator, the A register, okay? So load A with the particular value FF, okay? So the binary encoding of load A with an immediate is A9. Okay, so A9 is the instruction for load A with an immediate. Okay, and so that's what I'm loading, and then what is the FF that's right after it? What I'm loading it with. Okay, so yeah, okay, so every instruction, so this is one thing that's nice about the 6502 assembler. The opcode for every instruction is an 8-bit thing. Okay, so if we have 8 bits for an opcode, how many theoretical opcodes operations could we have on this on an architecture with an 8-bit opcode? 256. Okay, not all of those are used, so only about 100 and something of them are used. Okay, and the ones that aren't used are illegal operations that thou shalt not use. Okay, now on the original 6502, some of them were illegal and undefined secret opcodes. And so the way you want to kind of think about some of those is like, have you guys ever seen like on Facebook or various, it'll get passed around like the secret menu at different restaurants where you can you can go to Steak and Shake and if there's a secret menu that they don't, you can get stuff that's not actually on the menu if you know what to ask for, right? So the opcodes, some of these unused opcodes on the original 6502 were kind of like that, right? Some of them did like really weird stuff and stuff that you shouldn't use, okay? But some of them were kind of secret menu. And you could do kind of interesting things with them. The 65C02 and later versions of it, okay, basically corrected so that any of the illegal opcodes are just treated as no ops. Okay, so you can't pull that game, okay, on this guy. If you use an illegal instruction, it's just ignored. It's treated as a no op. Okay, fine. All right, so now for the rest of these instructions, right, if every opcode is 8 bits, then, and this is one difference between this and ARM, how long was every encoded operation, opcode, operand, everything on ARM? Every instruction was exactly how many bits wide? 32, okay? Asterisk, there was one exception to that, but basically they were all 32 bits wide. Every single instruction, okay? Regardless of what type of instruction it was, okay? So for example, if the instruction was to return from a subroutine, okay, or RET, right, we didn't necessarily need all 32 bits to encode that, but we had to use 32 bits, okay? So in that sense, we were wasting memory. On the other hand, though, it meant that literally every instruction was the same width, and that can speed other things up, okay? Now, on ARM processors of today, right, do we have to worry about how much RAM we have or how much memory is on the machine? No, there's way more of it than we could possibly actually use. Okay, and which is why it's okay to be wasting data on some instructions. Now, if we go back in the day, though, the 6502, this era, memory was extremely expensive, particularly RAM. Okay, and so because of that, we wanted the architecture was designed in such a way to be as minimal in terms of memory usage as possible. Okay, so not every instruction is the same length here. All the opcodes are the same length, but the operation encodings themselves could be longer or shorter depending on what they're doing. Okay, so for example, if I want to load the accumulator with the number FF, how many bytes do I have to use to do that? 2 bytes. Okay. A9 says I'm loading the accumulator with a particular value, and then the value, right? Okay, so A9 encodes load accumulator with a specific number. What number? FF. It can't be because it's an 8-bit processor. Right. Because the accumulator can only hold 8 bits. Sorry. I mean, you have to remember, right, that the design of this processor is early 70s, right? Early to mid 70s. Yes, you don't have all of those. Okay. Partly because, I mean, so there are logical shifting operations, but in terms of like, if I wanted to load -1, right, I would, the reason we had to go through that rigmarole is because everything had to fit into a 32-bit instruction. Here, if I want to load -1, well, what is -1 in hex, by the way? It's FF, right? In 2's complement. Okay, so the move Z, move N, move K, all of that business that we did with ARM, we don't have to worry about that, okay? Because our instructions can be as long as they need to be in order to actually encode the data, okay? So that's one advantage of this over ARM. The disadvantage is it means that every instruction does not take up the same amount of data, okay? Because what is our first instruction in this program? Load A with all ones, right? So in our hex dump, that's the A9 and the FF, 2 bytes. Okay, what about the next instruction? STA, what is that going to do? Store A. Okay, so if load A takes a value and puts it into the accumulator, then there ought to be an instruction for taking the accumulator and putting it somewhere in memory, right? Makes sense, right? In the same way that we had LDR and STR in ARM, right? This is kind of the same thing, okay? Well, where do I store data? Some memory, and memory addresses are how big on this architecture? 2 bytes, which is how many bits? 16 bits, right? 8-bit data, 16-bit addresses. This is why, how many address lines did you run when you were wiring all this stuff up? Because it's a 16-bit address bus, right? Yeah, it's like almost like this stuff all makes sense. Yeah? Okay, ddrb. Yeah. Okay, ddrb is a macro. So look up at the line number 3. Okay, what has been done there? Right, okay, so 6002 is a memory address, and that's where we've wired in the ddrb, okay, which is the data direction for bus B register on the 65C22. Okay, so it is in we've mapped it into memory, and I have defined here that ddrb is a placeholder for the value 6002. What this means is that anytime in my program that I want to address the data direction bus for or register for bus B, I can type ddrb instead of having to remember that it's address 6002. Well, that's really handy. Yeah. Well, hopefully it'll print hello world to the LCD. Oh, okay. So let's think about the schematic, the architecture here, right? What do we have running between the processor, the RAM, the ROM, and the 65C22? There are 3 things, okay? There's a data bus, there's an address bus, and there's some control lines, right? Okay. How big is the data bus? How many bits wide is it? 8, right? 8-bit architecture. How many address lines were there? 16-bit address space. And then the control lines, there were however many there needed to be, depends on the chip, okay? So the 65C22, you can think of it as being like a middleman, okay? On one side of it, it has control lines, data lines, and address lines, okay? On the other side of it, so it's connected to the data bus, okay? And then it also has some control lines that are somewhat related to the address bus, but it's not like it ever all. So like the how many address lines are actually connected to the 65C22? Not all of them, okay? So it sits in the middle between the processor and the LCD, okay, or any other peripherals that we chose to put on here, okay? And in our case, what are the peripherals? Our LCD and that little series of 5 buttons, okay? So the middleman, well, let me just load the schematic. It's probably the easiest way to do this. Yeah. Okay, so here is the 65C22, okay? And so what is connected to that? Well, what in the middle of it on the left, we've got D0 through D7. So what are those? Yeah, those are the data lines, okay? And then here for RS0 through RS3, we have some of the address lines connected to that. Not all of them, but some of them, okay? And then we also have some other lines coming up here to chip select 1, chip select 2, read, write, interrupt request, phi 2 for the clock, okay, reset, and so on, okay? So those are basically data and control lines for that chip. On the other side of it, what do we have? We have PA 0 through 7 and PB 0 through 7, okay? And what are those going to do? Those connect to the peripherals, okay? So looking at the B, okay, so peripheral set, which ones is it? B connects to 8 of the data lines on the LCD, okay? So data gets sent to the LCD over the data bus, then the chip takes it and passes it on to its B bus, which has the LCD on the other end of it, okay? And then there are 3 more lines that are for E, read, write, and reset on the LCD, and those, we're out of pins on the B bus, so we have to use some of the pins on the A bus, and that's what those 3 are going over to, okay? So it is the middleman between the processor and the 2 peripherals. And right now, for this machine, our peripherals are buttons and the LCD. That's it. Okay. On the Commodore, our peripherals would be things like the disk drives or the sound chip or the other kinds of things. Okay. And so the Commodore actually has several of these peripheral chips on it. Okay, we've only got one here. The C64 has like 3 or 4 of them that are used in various ways. Okay, one of them controls, for example, the keyboard. That would seem useful. There's the 2 joystick ports that are on the side. Those got to get controlled. Disk drives, the tape drive, the screen, right? A lot of other peripherals that we don't have on this simple breadboard machine. 2 per chip, basically. Okay. Or yeah, you could have more. It depends on how many. Like if all we wanted to do was have buttons, you could have 16 of them, right? Because you got 16 lines. But obviously we need more than that, right? So we're using basically 11 of them for the LCD and the remaining 5 for 5 buttons. And that's all we've got, right? So if I wanted to have additional devices, we would have to have a second 65C22 and wire it up also. And now you can see why do you think you don't put computers together with breadboards? Because what happens very quickly? It looks like that, right? And it starts to look like a rat's nest. Well, right, here we are, okay? So this is why real computers are made with PCBs, right? Where all of this stuff would be soldered to a PCB, and these wires are actually metal traces, some of which are hidden inside the PCB if it's multi-layer, and you can't see them, okay? Yeah, so like a motherboard, right? A modern motherboard is going to be 4, 6, maybe even 8-layer deep PCB. And it takes specialized equipment to fabricate these things, which, right. But, we're looking at what computing looked like in the 70s and 80s, right? That's what this whole course is about, right? And I feel like we ought to do have various 80s synth pop music on in class every time we're running. Although I'll probably get DMCA strikes on my channel. Hmm? Yeah, that thing is a hot mess right now. Yeah, we'll deal with it later. Yeah. Okay, so in order to send data to the LCD, right, we have to send the appropriate instructions to the 65C22 to tell it, hey, I want you to send data to the device rather than get it from the device. And then I also need to say, well, what data am I going to send there? Okay. So if we go back to our program, okay, the second instruction here is to store what's in the accumulator to the memory address ddrb, okay, which ddrb was a placeholder for 6002, okay? So ddrb is the data direction register for bus B on the 65C22, okay? And what is connected to bus B? The data lines in the LCD, yeah? And so we want to send data to them. And so we want to write to those, not read from them. And this is why we're sending all ones, right? We're sending all ones, basically saying all 8 bits of the B peripheral lines, I want to be outputs. Okay, so I set them all to ones. Okay, and then I need to store that all ones to this address in memory. Okay, now let's look at the hex dump here, 8D0260. What is that? Okay, that's the next 3 bytes, right? Yeah, okay. So 8D is the instruction for store A. Okay, and now where are we storing A? To a memory address. Okay, which DDRB was a placeholder for 6002. Okay, well look, 0260. That's the memory address, okay? Because it's written in low byte, high byte order. Yeah? Wow. It's almost like this stuff's all coming full circle. Yes, and it would encode exactly the same way. Okay. Now, what's the benefit here of using the DDRB macro? Variables are nice, right? If you haven't learned that lesson already, then exactly. Okay. So yeah, we're basically treating it as a variable. Okay. Yeah. Okay. So, but yeah, it would encode the same way. Okay. Then what follows that? So what's after the 3 things that I've got highlighted? Okay, A9, we're loading the accumulator with what? Can't fit ADE0 into the, just E0, because how much data can fit in the accumulator? Just 8 bits. Okay, so what you've noticed here, you see how the first two instructions have how many bytes did it take for the first instruction? Took 2 bytes. How many for the second? 3 bytes. So not every instruction is the same width. Okay, make sense? This means that the encoding or the amount of memory it takes to store a program is almost as tight as we can possibly get it. Okay, which is a good thing in the 70s because memory was expensive back then. Okay, in fact, what did memory look like in the late 60s, early 70s? If I showed you guys a picture of this stuff, I probably should. Okay, so before RAM chips, there was this stuff. Oops, that's not what I wanted a new tab in. This is what memory used to look like. Okay, this is called magnetic core memory. Okay, so you've ever wondered why things are called core dumps? You're looking at it. This is core memory. Okay, and the core refers to, so you see this? There's a bunch of wires crisscrossing through iron rings. Okay, and when you send electricity through these things, it magnetizes the rings in one direction or the other. And then when you want to read from it, that will induce a current or not induce a current into the wire. And you, by knowing and setting all the grid stuff appropriately, you can read right from the correct locations. Basically, yes.
And then based on
based on how it's magnetized, that's how it stores the data. Okay. Now, that's kind of annoying though, because look at all these little metal rings. Yeah. Well, okay, yes, but if there's nuclear explosions and electromagnetic pulses, I think we have bigger worries than whether or not our computers still work. Okay. Oh yeah. Well, yes. Okay. So yes, this stuff was very expensive. Now, why do you think it was so expensive? Yeah, a lot of this was done by hand.
And then you have people that would mess up. You have somebody that messes up 2 of them and wastes like days of work.
Well, that happens. Okay, but on the subject, who would have been making this stuff? What does this remind you of? This yeah, this is like textile weaving, right? And so yeah, a lot of the people that did this were high skilled people that had experience in the textile industry, which is to say, ladies. Okay, it was probably a lot of women that were making this stuff. Okay, because they had the experience necessary from textile work to do this kind of small scale weaving, if you will. And it's effectively what they're doing, right? Okay, so because memory, and this stuff stopped really getting used in the mid 70s or so, right? Because memory was so expensive, the replacement for this, RAM chips, was also horrendously expensive. And so it meant that your machines had very, very little RAM. And as such, you needed to have your programs as tightly as possible stored in memory. Oops. Well, no, because we don't need to. The advantage is that all of your instructions are the same length, which makes it faster to access. because you don't have to calculate how much data to be pulling in. You know exactly how much to pull in at every cycle, right? So it's a trade-off. That's completely different. That's all the art. The program part is very small. The reason Call of Duty is hundreds of gigabytes is art. Well, yeah, but then if somebody else is wearing that skin, then you wouldn't be able to see them wearing that skin.
Just replace it with
Then why would they buy the skin? Yeah, they want to show off to you that they got that skin. Yeah, but okay, but you aren't the customer here. Yeah. So, okay. All right, so back to this thing, right? So what do we notice here? Our instructions are kind of coming in sets of two: load A, store A, load A, store A, okay? And there we go. We got all of this stuff, right? Okay, now, this is obviously not a very efficient way to write it, but how much data do I have here? Can't count that high. Okay, we have 32K worth. And here is the second to last set of bytes. That's our reset vector, 8,000. And then we have this extra padded 0 just to make it fit into 32K. All right, so now what do I need to do with this thing? I need to write this to the EEPROM. Okay, so pull the EEPROM out of the socket. Right? Well, because I want to write to it. Put it into the EEPROM programmer and pray that it works. Okay, so okay, then I just need to remember the command to write to the. All right, hang on one second. Okay, so hang on just one second. Okay, so now that I have the image, how do I write this to my thing? Okay, it's MiniPro, and then this is a program, an AT28C256, and we're writing what image file? Well, it was a.out because that's what came out of our assembler, and so it is now accessing the EEPROM programmer. It's writing the data to it. It's double checking it, and it's good. Okay, so now we pop our EEPROM out of there and plug it back into the, okay, Cole, I think, yeah, okay, you had it this way. Lock it into place. Switch over to the webcam. Okay, and then, okay, and now the moment of truth. Theoretically, yes. I'm going to speed the clock up. Nope. That would be why. Well, actually, no, it can execute code without the RAM chip here because we never used subroutines or anything like that. And so it can still technically work without the RAM chip. The RAM chip, and hopefully the rest of it will work. Okay. Drake, do you have yours with the LCD? All right, well, let's see it. Now I'm going to have to reprogram your EEPROM, but oh, well, I'll show you in a minute. All right, let's see it. Yep, I need the barrel plug and the.
I know Shane's on there somewhere.
Yeah, he's on the screen. Okay, so barrel plug, please.
Just throw it. Yeah, up there.
Okay, so positive is orange and negative is yellow. Yeah, it should. Okay, right. So now it's not going to do anything yet because I need to write the image to your EEPROM, okay, which I'll do that. Okay, so I'll do the same thing. Okay. Um, okay, I do have one idea. No, because it should, when you power it on. Okay, now let me be clear. You have your pin 1 facing to the left, correct? Yes, okay, that's how I expected it to be. Okay, well, yeah, so it should still work though, even without the RAM, because yeah, but everything's powered because nope. Okay, well, Drake, let's try yours. Why not? Control lines? Okay.
Because like this one here.
Oh yeah, this is what's going to control everything. So yeah, it won't do it. Okay, so now this is the whole point for the Arduino. Okay, because if we take the Arduino and we plug it into the data and the address and the read write line, we can see what data should be going on to the bus. Okay, so for the sake of time, I won't do this right this instant, but that program on the Arduino, right? So if we took Evan's thing, okay, and plugged the Arduino all into the appropriate pins, we could see what was on the data bus and what was on the address bus and see if the CPU is at least correctly accessing the data and trying to execute it. Okay, that will tell us, amongst other things, is it that he miswired the 65C22 or some other problem? probably not going to be the issue, but throw them in, right? The capacitors. Okay. That's probably not going to be the problem, but it on every power rail you want to bypass capacitor, yes. So I doubt that's the issue, but it could theoretically be one. Okay. All right. Do we have any others that we can try? No. It, you're gonna have to move stuff. Yeah.
I think I just have to move the EEPROM.
Yeah. So this is the downside of me putting the socket in here, is because it's really crowding the board. Okay. But I put the socket in here because otherwise you'd have to be shoving the EEPROM into the holes and using a flathead screwdriver or the chip puller to pop it out. Well, the socket's way easier than that, right? That was the whole reason I got them. So, but it does mean that the wiring is getting a little tight. Okay, and sorry, them's the brakes. Okay. Okay. So then let's go back to the code just for the last minute here. Okay, because this particular set of code is probably the most monumentally inefficient way to write hello world. Okay. So what we would want to do then, a better way to write it would be like so. Okay, and this is where the RAM is going to be required because it's going to use subroutines. Okay, the other thing is in the same way that we can define, you guys remember on ARM where we had ASCII strings and we could define them like so? Well, we can do the same kind of thing. Okay, so if I tried to assemble this as is, it's going to complain because what do I need to change here about bin's source code? What do I need to change about bin's source code for the new version of the assembler to work with it? The dots. Okay, so .org should become org and so on. But other than that, it's basically ready to go. Okay. Now, the last thing though is this particular version of it, which is tighter and cleaner, will only work if it if the RAM is also working. Okay, and the reason is because it uses JSR and RTS, jump to subroutine. Okay, jumping to subroutine requires what? Okay, how do I, like an ARM, if I branch and linked to something, what happened when you hit a branch and link instruction? It's different than just branching, okay, but what happened, what was in a subroutine, what was the instruction you had to put at the very beginning of a subroutine in AR64? You had to do STP, X29 and X30, right? You had to push those onto the stack so that at the very end of the subroutine, you could pop them off the stack, okay, and know where to go back to, okay? Now, on ARM, the stack is much more tightly controlled, and for the subroutine call also pushes the appropriate data onto the stack. So JSR is going to jump to a subroutine and push a value onto the stack so that you can pop it off at the end with the RTS. Okay, but in order for the stack to work, the stack is a piece of RAM. The RAM chip's got to be there and correctly wired up for this to actually function. Okay, for subroutine calls to work. Okay, so does that make sense? All right, so some of you guys have some debugging to do, but this is how you can test whether or not your thing is working, is if you pop it in and bam, hello world appears on the screen, and you might adjust the contrast a little bit. It could be the case that it was turned up too high or too low, and that hello world actually was there, we just couldn't see it. well, after class. But yeah, so like try that, right? And then the next thing would be connect your Arduino to it and using the serial monitor program, see what's going on, okay? And if it looks like it's trying to send hello world, right? Like you're seeing the correct instructions and the correct data, okay, then you know it's actually trying to execute it. It's just not able to for some reason, okay? So, yeah, there you go. Okay? All right. See you guys Thursday.